let me just recap what we did yesterday. So we talked about this problem of diffusion or Brownian motion. So basically we are describing this, you have this particle or just one particle. So they move randomly, and what is the probability? So we define this P of xt. So this is the PDF, probability density function. So it means that P of xt dx, so this is the probability of finding the particle between x and x plus dx at time t, right? So then what we showed that this probability satisfies this equation. So this is in one dimension, but if you can generalize easily to higher dimensions, so it just becomes a Laplacian. So it satisfies this equation. And we also showed that, okay, so for general diffusion is, okay, this diffusion coefficient depends on whatever the properties of the system. And if it is, if you are describing a particle, let's say in water, motion of a colloidal particle, so which we call Brownian motion, so then what we saw is that gamma is basically given by kVt by, d is given by kVt by gamma, right? So then, what we saw that this, you can solve this equation exactly. And what is the solution? So solution is given by, so minus infinity to plus infinity, integral over all initial position, P of x0. So that's the probability of, that's the initial probability distribution for the finding the particle, times xt x0 0. So this we call propagator, right? So this is the propagator. It means that, okay, suppose this initial condition is a delta function, right? So then this is the probability of finding the particle at x equal to, at x at time t. So for example, if it is, if P of x0 is delta of, let's say, if P of x is, let's say delta of, so what do you call, x0 minus some, okay, P of x is delta of x minus x0, right? So that means P of xt is just g of xt x0 0, right? It means that, okay, so basically when you start, so this is the initial distribution, let's just call it P0. So this is the initial distribution. So if, let's call it P of x0 is something like, okay, y, right? So this is, right? So it says that, okay, if you start this particle from some position y at time t equal to 0, so this is the probability density of finding the particle at position x at time t, right? So we also showed that the g of xt given x0 0, so this is 4 pi dt e to the power, so exponential of minus x minus x0 whole square by 4 dt, right? This is what we did yesterday. So next, what we showed or what we discussed is that, okay, so this is the description at the level of probabilities, right? But then you can also describe this system at the level of trajectories. And if you want to describe this system at the level of trajectories, so then what we said that this satisfies this equation, dx dt is some noise, right? So that's the equation at the level of trajectories. And this noise has the property that this mean is 0 and is equal to 2d times delta t minus t, right? This is what we did. So we also said that, okay, so this you should think of it, this equation like when you want to, for example, if you want to do a simulation or something, right? So you have to discretize this. So how do you discretize it? So you should think of it like, okay, del x del t is noise now at the time t, but it's at the, this noise now at the discretized level, right? So it's, so this noise satisfies again this one, and delta t, let's call it again t prime. So this is at two different times at the scale of this delta t. So this is equal to delta t prime. So if they are not equal, then this is equal to 0 times 2d by delta t, right? And we say that, okay, if you take a delta t going to 0 limit, so basically that corresponds to that equation, right? So also what we say, sometimes it's, so this is, so we say that this is a noise, so we say it's a Gaussian noise, so the distribution is Gaussian with a variance which is given by this, right? So sometimes you can also take out the strength outside, so then you can define it a unit variance. If you take out the strength outside, so what you see is that, okay, this is equal to, so what is the strength? So the variance is this one. So what will be the strength? So root over 2d by delta t. So now you will have some other random variable. Let me just call it eta. Okay, eta at the level of delta t. Okay, so then this is 0 and t prime, so this is just delta t prime, right? So basically, so this is a random variable drawn from, okay, so it's basically says that p of eta is given by square root of 2 pi e to the power minus eta square by 2, right? So if you are doing a simulation, basically this is how you will evolve. So where eta is drawn from this distribution, right? So you see that basically that equation you can write it now delta x. So let me just write it here. This equation, let me just write it here. So it is that delta x is equal to square root of 2d delta t eta of delta t, right? So it says basically that delta x scales like square root of delta t, right? So usually if you have a velocity, you see that delta x scales like delta t, right? If you have dx dt equal to velocity, but here delta x scales like square root of delta t. Okay, So this is what we did, and did we do something else? Okay. So now, so let's do one more exercise, because I know now how. So what is this one, right? How delta x scales with delta t, and this is a noise with unit variance. So I should be able to compute this probability directly without going through this step, right? So you remember yesterday Abhishek did this generating function method, right? So you had this, so he wrote down this equation x n plus 1 is equal to x n plus this noise, right? So this is exactly equivalent to this equation, right? So this one is like, right? So this is exactly equivalent to this equation, right? So you now remember how he computed this distribution of x by various ways, right? So one is combinatorics, then other is using this generating function, right? So let's try to just compute this using this generating function. Okay? So what is this object? So let's forget this one. So now what are we interested in? We are interested in x t, right? The distribution of x of t. So what will be the distribution of x of t in terms of this one? So this is your time, right? So you are breaking into steps of delta t, right? So this is, let's say, 0, this is your t, and this is your delta t, right? So there are n such time windows. So then this x of delta t will be 1 to n. So this is, let's say, 1, this is 2, this is n, right? Delta x, let's call it I. So this is the delta. So this is, first one is, let's call it delta x1, then let's say delta x2, delta x3, delta x4, and so on, right? Delta xi. So with the constraint, so such that, so what is n? N is some arbitrary thing, right? Now, so what is given is basically t, right? So delta t and n, something which we have just put in, right? So finally what you have to take, delta t, you have to take it to 0, n we have to take it to infinity, right? Keeping n times delta t equal to t fixed, right? So let's first look at this one and try to calculate. So it's one of the easiest way to calculate this one. So it's looking at, so if you want to, so finally what do you want to calculate? We want to calculate p of xt, right? But one of the ways to calculate p of xt is, but first not calculating p of xt, but looking at its something called characteristic function. Okay? So let's look at so what is a characteristic function? So this is the average of ikx. Right? So it's essentially the Fourier transform, right? What we did yesterday. So what is this object? So this is essentially dx e to the power I kx p of xt minus infinity plus infinity, right? So this is what we did last time, right? So when you in fact solve this equation, we use this Fourier transform, right? So you see this connection basically is how we do. So okay, so this one now, so I'm going to write it in terms of this object, right? So what is this? E to the power I, okay, let's k. So let's call this something j, right? This equal to 1 to n delta x I, so delta x j, right? So now, so these steps, so these are the steps, right? So these steps are uncorrelated. So they are independent of each other, right? The steps you take at one time and you take at another time, they are independent of each other, right? So therefore, okay, so let's write it one more time and then, so this one of course, okay, if you have a exponential of a sum, you can write it as the product of exponential, right? So this is of course j equal to 1 to n e to the power of I k, and delta x I we can just replace by this one, right? No. So it's delta xi is square root of 2d delta t, and eta, let's just call it eta I. It's basically, okay, so it's essentially like, okay, I is j, there's eta I there, right? Right? Is it clear? So I'm just doing two steps. One is, okay, so this basically what I'm doing. Okay, so first time delta xj. So first step is this one. Okay. So then what I'm doing is that, okay, j equal to 1 to n e to the power of I k, and this delta j I'm just going to replace by this one. So this is square root of 2d delta t times eta of, so delta j is delta t, so I'll just not keep this subscript delta t, and I'll just put a j saying that this is the noise act at the jth step basically, right? But this noise at various steps, they are uncorrelated, right? So these are essentially the jumps. So therefore, this, the expectation of this product is same as the product of expectation of each quantities, right? Is this clear? Right? So that comes from the fact that these different etas are uncorrelated. Okay? They are independent of each other. So therefore, what we have, I k x is equal to 1 to n to the power I k square root of 2 d delta t times, right? And also this, all this noise at various steps, they're drawn from the same distribution, right? So it's, the distribution is independent of which step you are taking. So in fact, this is something, this to the power n, right? So I don't have to compute each of them. I just compute one of them and raise it to the power n, right? So this is in fact equal to, so this first one, taking this thing out of this, comes from the fact that these are independent of each other, right? So these are, and this second step, these are identical, right? So these are called, so these etas are called basically identical and independent and identically distributed random variables, right? So they're independent and they're identical. So this is I k to the delta t eta. I'll just forget about this subscript to the power n, right? So we have to basically essentially compute this quantity. So this is essentially okay. So this guy is, if you call it something like kappa or let's call it lambda. So it's essentially the generating function of this noise, right? Characteristic function of this noise. So what you have to compute is I lambda. You have to compute this. Right? But this is something easy to compute because I said that eta is drawn from Gaussian distribution. So show that this is equal to minus lambda square by 2, right? So then what is the characteristic function there? So this is homework, right? So given this distribution of noise, this one, so that this is equal to that, right? So given this, what is this one? E to the power I k x is equal to e to the power of minus d square, so k square is this correct? Lambda square. Delta t by 2 times n, right? Times n. But this one now I can combine, and what I get is e to the power minus k square. Now is this one familiar? Because this is what you got last time, right? So in fact, so this is the characteristic function of a Gaussian random variable, right? Because that it's essentially same as that one, no? If I say that this is the characteristic function of this one, so this both they have the same form, right? Except what is this lambda? So if you just if you want to write it in this form, so it's essentially this 4 lambdas. So I can just write it in this form, right? So what I think e to the power minus half, then okay, it doesn't matter. Yeah, it's essentially this one, no? Square root of so you see that, so this always the characteristic function of a Gaussian random variable, it has this form. So so therefore this x, so this is the characteristic function of the full x, right? So what should be the distribution of x then? Gaussian again, right? So it says that xt is again Gaussian, right? So, okay, let me just write it here. So if you have a distribution, let's say p of x, which is 1 over square root of 2 pi sigma square e to the power minus x square by 2 sigma square, right? So this one, the characteristic function is e to the power minus sigma square e square by 2. So here this is the case where sigma is equal to 1, right? So what is the sigma here then? So if I want to put it in that form, so what is sigma square? So for this one, what is the sigma? So you have k square dt, right? So this is, you are supposed to write it sigma square k square by 2. So what is sigma? Sigma square is 2 dt, right? So therefore, what will be the distribution when you get it back? It's this one. So 1 over square root of 4 pi dt e to the power minus x square by 4 dt. Okay. So this is because I have taken x0 equal to 0, right? So if you don't take x0 equal to 0, so there will be a term here, right, initially. So it's not only the noise plus that x0 term, right? So this is in fact x minus x0 has this distribution, right? Because this is, I'm summing up only the jumps. So that only gives me the displacement. It's not the position, this is the displacement. So if you want the position, basically, so this x will be basically x minus x0, right? So there, so x minus x0 is the displacement, right? Or in other sense, okay, in some sense you can just think of like putting x0 equal to 0. So this is actually is a very nice way of calculating thing, and it's quite actually general. So you'll see that this way of computing, like usually, I mean often when you want to compute this probability distribution function, not only in this problem but in various problems, so often calculating this PDF is harder, so, and it's easier to compute the characteristic function. Here you saw that when you compute the characteristic function, it becomes decoupled, right? So it just becomes this product of this function. So it's easier to compute. Okay. So this is that. So now, so in fact what we have also found in this calculation, so it's a very nice property, right? So what we have proven that if you take a sum of random variables, so this is a sum of random variables, right? So if each variable is distributed according to a Gaussian distribution, then the sum is exactly Gaussian. So in fact, if you can take any sum, a n, let's say xn, n goes from 1 to n. So ans are some coefficients, right? So it's in fact ans are, you can just think of it like variance, standard deviation. So strength of this. So it says that if you take any combination, linear combinations, if xn's are distributed according to a Gaussian distribution, then the distribution of S will be also Gaussian, right? So this is very important thing to remember, because then you'll see that if you have a, so finally if you can put something like this, then you know that if the distribution is Gaussian, so you can immediately write down the distribution of this by just knowing the, so Gaussian distribution is, why is it, I mean what is very special about Gaussian distribution? So you need only two cumulants to describe this Gaussian distribution, right? Just the mean and the variance. Yeah. it doesn't matter. So that's what I'm saying, right? So because, see, I can always put this, so that's why I put this, so I could have written like that, right? So now let's say this xn's are Gaussian, but it has different variance, right? But all these variance, I can just take it out and just put, let's call it sigma n here, right? So now all these xn's are Gaussian distribution with unit variance, right? You can always scale out the variance, even it might even have a mean, right? So you can again take out the mean. So let's just do this. Okay? So let's say this is xn. And xn, so I can always write some sigma n Zn plus mu n, right? So then what is this Sn? S is just, okay, n mu n plus right. So this is the mean S, because I scale it out such that, so mean x is equal to sigma n Zn plus mu n, right? So this mean is, this is equal to 0. So that the mean is basically this one, right? So I just scale out the mean. So now, so therefore what is the mean of S? It's just this one, because this, the mean, so this Z I have chosen such that the mean of these Z's are 0, right? So therefore S is n mu n. So now instead of studying this S, so I can always look at a different variable which I just shift by the mean, right? So I just call it R, so which is S minus this object, right? So if I know the distribution of R, I can find out the distribution of S. That is just a shift, right? So what is the, now what is R? So R is just n sigma n Zn. So now, therefore, I want to find out what is the properties of this random variable, right? So I'm saying that now, so I have already scaled out this variance. So now, if Zn's are drawn from a Gaussian distribution, what is the distribution R? So that you can immediately see, because again, if you do I, K, R, right? So this time they are not, these each terms are not identical, they are still independent. So there will be n of them, 1 to n e to the power I, K, sigma n, Z. But this object we have already computed, right? So what is that object? What is this object? If Z is a Gaussian random variable, right? So this is if P of Z is e to the power minus Z square by 2 by square root of 2 pi. So what is that object? So e to the power minus k square sigma n square by 2, right? So this is e to the power minus k square by 2, 1 to n sigma n square. So this is now my new variance, right? So what is the new variance? So let me just write it here. E to the power I k r is e to the power minus k square by 2, and let's call this thing delta square. That's my new variance. So what is delta square? So this new variance is just the sum of these variances, right? So then what is the distribution of R? It's just this one. Right? So therefore, if I know that I have a sum of random variables which are distributed from a Gaussian distribution, then the sum is also Gaussian. And what I have to know, so if I know P of R, of course I can find out P of S, right? So what is P of S? It's just this one, no? 2 pi delta square e to the power minus S average square by delta square, right? So therefore, if I have a sum of random variable where these guys are Gaussian, then the sum is also exactly Gaussian, right? And all I have to know is the mean and the variance. And mean and the variance is usually easy to calculate, right? From there, so how do you compute a mean? It's essentially this one. And variance, how do you compute? You just take square of it. Then this will be like 2 terms, right? And then you just compute the variance. So this is something easy to compute, right? So all you have to compute is the mean and the variance, right? So therefore, for this random walk case, so you saw that if you want to compute the P of xt, all you have to compute is the mean and the variance of x, right? And that's, okay, so I'm going back and forth the same calculations, but basically I'm just doing it various ways so that it looks familiar, right? So now what I want to show that since you're convinced that, okay, so now let's start with this equation, right? Let's start with this equation. So what is x of t? So I know that, okay, so let's look at this equation again. So dx dt is dt, right? Right? So what is x of t? X of t minus x of 0. So what is that? So this is just the integral of 0 to t right? So you see that this is the displacement. It's a linear combination of these noises. So this integral, you can think of it like a sum now, right? So I showed you how to discretize that integral to sums, right? So you can always think of it as sum. So it's essentially this displacement is some linear combination of these noises. And each noise is, when they are Gaussian, drawn from Gaussian distribution. So I know that this distribution of this is going to be Gaussian. So all I need to find out is the mean and the variance. So what is the mean? So let's call it y of t. So what is y of t? I can take the average inside. So that's 0, right? So this is 0. So this essentially 0 to t prime dt prime, and this is equal to 0. So this is equal to 0. So I need the variance. So mean is 0. So the variance is this one. So what is the variance? I have to multiply this integral twice, right? So what is this? 0 to t, let's call it dt1, 0 to t, dt2, t1, t2, this one, right? So now what is this correlation? So 2d delta t. So this one 0 to t dt1, 0 to t dt2, 2d delta t1 minus t2. So I can do one of the integral because of the delta function, and then I have one more integral, so that will give me t, right? So this gives me 2d t, right? So the mean is 0, variance is 2 dt, so p of x is essentially, p of y is essentially this one, right? This is what we call, right? So sometimes you see that basically you don't have to go through actually solving the differential equation. So if you know that if your system is linear, right? So you can just find out the distribution by just knowing the mean and the variance, right? And which is easier to compute than actually solving the differential equation, right? Okay. So how much time do I have? Okay. So now, so this is basically, okay, so I have showed you how to, for this system, how to compute this thing various ways. So let's look at in one more way, okay? So this is, remember that this is just a classical problem, right? There is nothing, it's just a classical particle, but there's this noise, and this noise is basically hitting this particle, right? Yeah. Ah. Okay. So let's go to this Gaussian distribution assumption. Okay. So before going to the other. So why I have been saying that this is Gaussian, right? Okay. So first of all, of course, it helps you to do calculation. Okay. But second, so what is the justification behind assuming that this noise is Gaussian, right? So let's look at this sum, right? Now even this delta x, so delta x, I could have again broken this delta x in small interval, right? So imagine that I'm just looking at now one of the small delta x, but I'm just dividing again in finer time. So then, okay, I have some sum, which is, let me just call this sum r only, right? Which is some sum of random variables, right? So this time, I'm not going to assume that this z is Gaussian, right? But z is some z's are drawn from some distributions. So you can also think of this r, you can just think of it like one of the delta x's there, right? Because even this delta x, I could have broken in finer intervals, right? Because even this one, I could have again broken in finer interval, and it's again a sum of some random numbers, right? Suppose I just look at this, and I'm now going to assume that these random numbers are not Gaussian. It has some distribution. Okay. So what is the distribution of R going to be? Okay. So I'm going to assume that now, okay, this, because you know that you can always scale out the mean. So I'm just going to assume that these guys have mean 0, because if mean is not 0, I can always shift it and look at around the mean, right? That's what we did, right? When you came from S to R. Okay. Also to assume that these guys have the same variance, okay, for just simplicity. So you can always shift it out. So this is something called, so I have this one. So where is this Z and so R, so these guys are IID random variables. So these are independent and identically non-random variables. Okay. So then there is something called central limit theorem. So which we are going to prove now. Okay. So again, so I am going to first look at the variance of this object. So what is the mean of R? 0. So what is the variance of R? So mean R is 0. What is the variance? N equal to 1 to n, something like m equal to 1 to n, Zn, Zm. Now these are independent. So they are going to contribute only when n is equal to m. Right? So this is same as equal to 1 to n Zn square. Right? So it has some variance. Let's say call it a sigma square. Right? So what is this? So sigma square n. Right? So this sigma square is not very important. I can just put it to 1. It's just a scale. Right? But so therefore, so if I have a very random variable whose mean is 0 and variance is this one. So what is the meaning of a variance usually? Just a spread, right? So now if I want to look at this variable at this scale, so it gives you a scale, right? So it says that, okay, this P of R is some distribution. I don't know yet what is this distribution, but assuming that, okay, it has some distribution. So this is 0, R, P of R. So it has some spread. So this spread is sigma, standard deviation, right? So in this case, the spread is basically goes like sigma root n. Right? So this is the variance. So now if I want to look at the probabilities of this object at this scale, at the scale of this, so I am going to define a new variable W, which is R by sigma. Okay. So the question is, what is the distribution of W? So I'm going to find out what is the distribution of W. Right? So this is what? This is in fact n equal to 1 to n Zn by sigma squared of n. Right? So I'm going to look at the distribution of W. So how do you find the distribution again? So we'll just look at the characteristic function, right? Can you see up to here? You should tell actually if you can see which is the line. Okay. So, okay, let me just write from there so that I have some space. So R by sigma square root of n, this is I equal to 1 to n Zn by sigma square root of n. So now I am going to look at this characteristic function. So again I am going to say that, okay, these are independent and identically distributed, right? So this is this sum, but I am just going to go to the last step and just, this was somewhere there, right? Yeah. So this is equal to e to the power of I k z by sigma square root of n. Right? Is this clear? I just keep this is equal to this, I put it there and it's independent and identical, so this is what I get, right? So now what is the properties of Z I need? Okay. So if I say that so how do you get a moment from a characteristic function? If the moment exists, so what is the moment? That's a mean. What is a mean? So mean is this one, right? So you see that if I take a derivative of this object, so what is this object? This is, in fact, let me just, so e to the power I k w, some random variable. So this is e to the power I k w p w dw, right? So what is the mean, for example? Mean is defined by w pw dw. In fact, nth moment is defined by this one, right? So now, so how do you get this right hand side from here? So you see that if you take a derivative with respect to ik, the derivative is going to act on only this function, right? So each derivative with respect to ik will bring down a w, right? So it's basically d ik of this function, and then after taking the derivative, you will put k equal to 0, right? E to the power I k w, and then you will put k equal to 0 after taking the derivative, right? So in fact, any moment will be given by this. Okay. So this is at k equal to 0. So therefore, if this function, if the mean exists, for example, right, this derivative must exist, right? First derivative must exist. Huh? So if the first derivative exists, so how does this function how should this function behave near k equal to 0? So e to the power I k w. So what is the function at k equal to 0? If I put k exactly equal to 0, it's 1. Okay. Now, so I'm going to expand this function near k equal to 0, right? So you might just think that, okay, this is just the expansion, I'm expanding this inside and just writing down, right? No. So what I'm trying to say is that, so you might just think that, okay, this is expansion is very easy because e to the power I k w is, of course, n equal to 1 to infinity. What is this? I k to the power n by n factorial times wn, right? And you might just think that, okay, I'm just computing this object, right? But that's provided this object exists, right? So this function always exists. But this exists means what? So this is a Taylor series of this whole thing, right? So this exists means this function is analytic, right? But it's possible that some moments exist and the higher moments don't exist, right? So that means that, okay, I cannot actually expand this power series, but in some cases maybe I can expand in up to certain powers, right? And then it becomes something like that. So for example, if the first moment exists, so first moment is given by the first derivative, right? So what should be that thing? It should be like I k w plus minus which one? So So dt ik, yeah, plus minus, which one is that one? Yeah, so minus dt of ik, I think it's fine, right? So then if I take a derivative with respect to ik and this higher order terms, so higher order terms is higher order in ik, right? So then if you take a one derivative with respect to ik, this will be some ik to the power something, and if you take k going to 0 limit, those terms will be 0, right? So if the mean exists, it must have this form, at least to the first order. Now if the second moment exists, so in our case, okay, mean is 0 by construction, but instead of w, suppose I would have looked at some s or something, then this term would have been there, right? So in our case, okay, this thing is 0 by construction. Now suppose the second moment exists. So how do you get the second moment? By double this thing. So in fact, yeah, so by double this thing, so this should be like ik square by 2 w square, right? Because if you take two derivatives with respect to ik, the first one will give you 2ik, so that 2 will cancel these 2. And then if you take one more derivative, it will give you ik, right? So these higher order terms now, so if I know that, okay, my first moment exists and second moment exists, so it must have this form, and okay, third moment, fourth moment may not exist. For example, let's say it's my symmetric function, okay, first moment is 0, second moment is exists, third moment is suppose 0 again, suppose fourth moment doesn't exist. So what should a kind of term, I mean, it should have? See, it cannot have a term. No, it might be infinity. 0 is exist. It might be infinity. Third moment is 0, let's say. So 0 means exist, okay, still exists, it's a number, right? But, okay. So if you take a function, so p of x, so which has a tail, for example, x to the power 1 plus alpha, it has a power law tail, right? So now, as x goes to infinity, right? So now depending on this power alpha, this alpha decides which moment exists, right? So what is the moment now? Let's assume that, okay, I mean, okay, it can be symmetric, doesn't matter, right? I mean, symmetric, if it is symmetric, then okay, third moment is 0 anyway. No, you can always put a normalization on this thing. So this is the tail, right? Yeah. So what I'm saying is, okay, so you can define a function, for example, let's look at this function. 1 by 1 plus x square 1 over pi. What is this distribution? Right? This is a normalized distribution. Is it normalized? This integral, if you do from minus infinity to plus infinity, what do you get? Huh? This is one of the integral usually they ask you in PhD interviews, no? They ask, so what do you get? So this is a, okay, so this is a normalized distribution. So now if you want to compute the second moment, so this is what I mean by, so this one goes like 1 over x square as x goes to plus minus infinity, right? The tail is like 1 over x square, right? So now what is this object? X square px So what is this object? So this will be minus infinity to plus infinity, x square 1 plus x square dx. Now you see that as x goes to both plus or minus infinity, both goes like x square, so it becomes constant, right? So therefore this integral will diverge. Therefore for this distribution, the second moment doesn't exist. Okay. So even if you compute something like this, for example, if you compute mod x ex dx, no? Even if you compute this object. So what is this one? 1 over pi, so roughly like x 1 plus x square dx. So both when x goes to plus infinity or minus infinity, it will go like 1 over x, right? Because there is a x square, there is a x there. So this integral roughly goes like, okay, let's look at the one side. So it will go like 1 over x dx. But this is log x, right? Log x, as x goes to infinity, it again goes to infinity, right? So in fact, this moment, mod of x, even this doesn't exist for this distribution, right? So similarly, and this one's always decided by the tail, right? For example, the tail is like 1 over x squared. So instead of that, suppose you have a tail, if p of x goes like 1 over x to the power 1 plus alpha, let's say as x goes to infinity, depending on alpha, suppose alpha is equal to 2, then of course second moment will, alpha is greater than 2, then second moment will exist. Alpha equal to 2 is like a marginal case because then you will have this log divergence for the second moment, right? And for alpha less than 2, of course, the second moment will not exist, right? Sorry? Yeah, see. So this is, so here, suppose alpha is, so this is a power, this is called a power law tail, right? So if alpha is greater than 2, then second moment will exist, right? Because second moment will roughly go like this integral x square by x to the power 1 plus alpha dx on both sides, but okay, I'm just looking at the tail at one side. So this integral will exist as long as, so this is, what is this integral? 1 over x to the power minus 1 plus alpha, right? No, is it correct? What did I do? Okay. No, sorry. Okay. So this one, so suppose alpha is equal to 2. So if alpha equal to 2, this 2 will cancel, right? So then still go like, it will be like dx by x, right? So it will be log, right? But if alpha is greater than 2, so then you have a tail which is faster than, so it will be something like 1 over, if alpha is greater than 2, you will have something which is faster than 1 over x, right? So that integral converges, right? So if alpha is greater than 2, your second moment will exist, but some again higher moment may not exist, right? But so far, okay, let's look at the second. So suppose second moment exists. So it has to be something like that. If fourth moment doesn't exist, so what should be the form here? It might be like, for example, suppose k to the power 3.5. Right? Suppose you have a function like that times whatever this thing. So this one, you see that, okay, if you take one derivative, take k equal to 0, this guy will give you something. If you take two derivative, still it's fine. Three derivative is still fine. If you take four derivative, this will go 1 over k will go down now, right? So now if you take k goes to infinity limit, this will go to 0. Or you can have some other divergence like log k times some log k or something, k cubed times log k or something, right? But what I'm saying is that it cannot be k to the power 4. It has to be between k cube and k to the power 4. Right? So it can have k cube log k or something like that. Or, yeah. But if your second moment exists, you can at least expand this up to this much. Right? So now in this one, so if my z is a random variable, so by construction I say that the mean is 0, the variance second moment exists, right? In mean is 0, so variance is the second moment in this case. So what kind of expansion I will have? 1 plus this guy is 0, mod z is 0 by construction. So what will be the third term? Third term is this one, right? So what is k? My k is now, this whole thing is k now, right? So what is this? That's right. So I k by sigma square root of n whole square, then half, right? And z square right? But okay, what is z square? It's just sigma square, right? So that's why I scaled it with sigma so that I don't have anything, right? Plus higher order terms to the power n. So what is this? Let's simplify. 1 minus k square, I square by k square by 2n plus higher order terms to the power n. This higher order term, if they exist or don't exist, this higher order term will be smaller than this one, right? Because this will be higher powers of this one. It might be some fractional power, but it might be higher powers of this one, right? So therefore, this n power will be n to the power 1 plus something. Okay? So these are higher than this term. But this one you know now. If you take n goes to infinity, so what is this? So it's exponential of minus k square by 2. Right? So then it says that this variable p of w, which is defined like this, in the limit n goes to infinity, is given by a Gaussian distribution. Right? So it says that if you look at sum of random variable, right, and you look at its distribution, right? So if you look, so let me just draw this picture now. So you have some sum of random variable, which is, let's call it R, P of R, it will have some distribution, right? So if you look at this, okay, it's here in fact. So if you look at this distribution at the scale of the variance, that's very important, right? If you look at this distribution at the scale of the variance, so it means that if you scale this random variable by this square root of n, then the limiting distribution is Gaussian. Right? It says the sum of random variable, if the mean and the variance exist, then if you look at the random variable at the scale of the variance, then at that scale, if the number becomes very large, it tends to a Gaussian distribution. So in this picture, what it means is that suppose I just draw this Gaussian distribution. So this is, let's say, the exact distribution of the P of R, right? So if I draw this Gaussian distribution there, so it will look something like that. So it will be like this, but then after that, this guy will basically go something like that. So this central region, so these are called this is the typical fluctuations, right? So typical fluctuation you assume at the level of the variance. So these typical fluctuations are described by Gaussian distribution. But there are of course these atypical fluctuations, right? And these are not Gaussian. Unless this variable itself are exactly Gaussian, right? So, but if they are not Gaussian, then this will be something there. So these are called large deviations, right? And this large deviation is something which is non-universal. So you draw from one, see this Gaussian, we did not have to take anything, right? I didn't tell you what is the distribution of Z. I only told you that its mean and the variance exists, right? So this is a universal answer. If the variance exists, then this limiting distribution, if you look at the scale of this square root of n, that will be Gaussian. But this large deviation function, there are a lot of interests actually computing this large deviation function nowadays, but this will be non-universal. Okay? But let's not go to the large division this thing. So this is the reason. So this was the reason, in fact, this delta x, right? So this delta x was this noise, right? But this each noise is again a sum of lot of noises, right? Because these particles are kicking this thing. So these guys are again as a sum of lot of noises, right? So that's why, so this noise we can assume it to be Gaussian. So that's the rationale behind taking that this noise distribution is given by a Gaussian distribution, right? And of course it helps you to do calculation, right? So now, what is the time? Okay. So let's, let me just give this. Okay. Yeah, but even then, see, even within that time, see this, what is the mean free time of this water molecule? I don't know, that's very small, no? What is just this thing? See, this time I was talking, did you calculate what was the time? This damping time, what is that time for a, this particle? Huh? Yeah, it's some nanosecond, right? 10 to 100 nanosecond or something like that. It is basically a nanosecond this thing. But this, what is the time, this mean free time of water molecules? It's much smaller, right? Huh? Hmm? Yeah, that's the time. So what is the, before it hits another this thing, it'll be like very small, no? Yeah. So then, even if you have this, if you look at this under damped time scale, even then this Gaussian time limit is valid. Okay. So let me just see, in physics usually it's useful to map one problem to another usually, because many things you know in one areas helps to find answers in another area, and there are always these connections, right? So here whatever we have been talking is, it's completely classical, right? It's just a classical particle in a medium, and this noise just coming from this thermal fluctuation, right? Temperature. But so this another area you have seen similar equations, right? So that's in quantum mechanics. Right? So quantum mechanics also you have a linear equation which is linear in time, and okay, you have something like that. Right? So that's the Schrodinger equation. So it's just a technical mapping, right? The physics is, of course, they are very different, right? The quantum mechanics here, this is it, right? There's nothing quantum about it. But you can look at this problem and actually, in fact, many things from here goes there and many things from there goes here, like path integral, for example, right? In quantum mechanics, right? So we'll come to that. Right? But let's say, what is the Schrodinger equation? So let's just right? And so this is the Schrodinger equation in general operator form. And if you write, let's say, in the free particle, because we are doing free particle right now. So let's do the free particle. And let's write down this equation in the position basis. So what is the equation? I H cross right? Looks more or less like that equation, but we can even do more. So let's take out this minus side on this side, right? And let's put this thing down. So what is that? So I'll put it here. So what do I get? Right? So this is the Schrodinger equation for a free particle. Now you see that this equation and this equation, they are exactly same. So what is the mapping? This I by H cross T in this quantum problem goes to T here, in this diffusion problem, right? So this is basically time you look at in an imaginary time. So this is something called, sometimes we call it weak rotation. And this diffusion coefficient there is here, H cross square by 2m. Right? So how do you, okay, let's not solve this because we have already solved this equation there. But this equation, this formal equation, what is the solution? So what is psi of t? E to the power minus I by h cross. So h cross goes down, minus I, h times t, psi 0, right? So this is the psi at time t, right? So now, also, yeah, so if you look at this one, this p is, in this case, is equivalent to psi, right? If you look at this equation and that equation, p is equivalent to psi, right? This equation and that equation. Okay? So what is psi of x? x, right? Yeah. Yeah, exactly. So don't think of it's, so these are mathematical analogies, right? See, at this level of mathematics, so you look at this equation and you look at this equation. Do you agree these equations are same or no? They are same. But this one, these are size, the amplitude if you look at in the real time. But we are now looking at this equation in a different time, right? Because this time I have taken it to this one. So I am looking at this equation in imaginary time, right? So now, so what is this one? So this is x e to the power minus I by h cross ht. And this one again I can write it in the position basis. So I just right? This is what you have. This one, what is it called? It's just a propagator. It's in fact this equation and this equation is exactly same. Right? So if you look at this one, so this one is, here is what? Tx0. So this one, if I just call it xt, x0, 0, this let's call it psi of 0, psi of x0. Right? Psi 0, x0, 0. It's exactly same as this equation. Right? So now we know that, okay, this guy we have shown this one. So let's see what is this propagator there. It's a free particle. Right? So what is this guy? X e x0, 0. This is x e to the power minus I ht x0, right? This is the propagator. So this one I should write down in the energy basis, right? So because in the energy basis I can actually evaluate this, right? So what is a free particle? So what is the energy? So what is the basis here? So I'm going to write down an energy basis. X k minus I ht k x0. So it's k prime, right? There are actually two integrals. It should have been k prime. But this matrix is, this is diagonal, right, in the energy basis, right? So only the diagonal element will be there. So what is the energy and what are the wave functions? The free particle, right? So what is this k x0? This is I k x0. Right? It's a free particle wave function, right, in the energy basis. And what is the energy? What is the eigenvalue? So in fact, in the energy basis, this becomes Ek, right? So what is the eigenvalue? What is the energies? So h cross square k square 2m, right? So okay, yeah. So now this problem, if I want to, so this is the problem in the actual quantum problem, right? But I want to now look at the time, which is this time. So this is of course true. Now I want to go from here to there. So what do I have to do? So I want to go from this problem to Brownian motion. So what do I have to do? So g of xt x0 0 I have to take this. There's a by h cross, no? Yeah. Yes. So I have to take this time I by h cross t, and that time I have to make my time in the classical problem, this Brownian motion problem, right? So if I take this one and go to this thing, so what will be the propagator? So this is exactly same. So this is of course dk xk. So this one will be k I by h cross t becomes t, right? So this becomes e to the power minus ekt k k x0, right? So this is, in fact, this is when it goes from amplitude to probabilities, right? Because this guy goes away, no? Now. So now this one I can compute, in fact, right? So what is this object? dk. So what is this one? E to the power minus I kx by square root of 2 pi. And so why do you need this square root of 2 pi? Normalization, because if you know that if you put t equal to 0 here, that should become delta x minus x naught, right? And so if you put t equal to 0, so this should become delta x minus x naught. And you know that the integral representation of is 1 over 2 pi e to the power I k, let's say, x minus x naught, which is 2, right? This one k what is this one? Okay, so in fact, I should have kept it. Okay, let's just keep it as t, because once you put it there, you can actually just contract this one, no? Right? So e to the power minus t h k. And this one, so what is the energy? A square squared k square by 2m. That's equal to a square square by 2m is d, right? So e to the power minus k square square dt, right? Then e to the power I k x naught. Right? So this is exactly your Fourier transform of this one, no? dk 1 over 2 pi e to the power I k minus I k x minus x naught e to the power minus k square dt. And you know the answer. So this is equal to e to the power minus x minus x naught square by 4 dt square by 5. Right? So it says basically by knowing this quantum mechanics problem, right, you can just find out your Brownian motion, right? So, okay, maybe tomorrow we'll do the rest. Yeah, so you can see that, okay, quantum mechanics again, you know that this propagator, there is usually a interpretation of a path integral, right? So this guy is essentially, what does it mean? It says that, okay, the interpretation is that the quantum mechanics goes from x0 to x in time t, right? So this basically the amplitude for this path, right? So there is a similar thing in here also. In fact, I think it was initially here and then it was, path integral, for example, I think it is Wiener which initially started, and then in terms of this Brownian motion, and then Feynman and later basically said, okay, you can apply it to quantum mechanics, right? Okay, so today I'll just stop here.